I'm here to talk to you guys about ionic bonding versus covalent bonding. All right, and we're going to start off with ionic bonding. And ionic bonding is made up of a metal and a non-metal. Okay, we've done the periodic table already, and so we've already done the oxidation numbers, which are the charges that those atoms will become when they become ions. And the staircase is the thing on the table that separates the metals and the non-metals. So the metals are to the left of the staircase, and they form positive ions called cations. The non-metals are to the right of the staircase, and they form negative ions called anions. So that's going to be very important when we're talking about ionic bonding, okay? Because ionic bonding involves a transfer of electrons. So one is going to give up, which is the metals, because they lose electrons. They're going to form positive ions. The non-metals will gain electrons and form negative ions. So to look at that from a Bohr model perspective, it would be like if you had, fluorine, and I'm just going to do its outer shell. It has 7 valence electrons in its outer shell, all right? And then you've got sodium, and sodium, its first shell has 2 and its second shell has 1. So sodium wants to lose an electron, because if it loses an electron, then it's going to look like helium, because its first shell is full. So it actually transfers this electron over to fluorine. When it does that, it becomes a +1 ion. But sodium is happy as a +1 ion because now it has the same outer shell as helium, which is a noble gas. Now fluorine gains an electron. So now it has 9 protons and 10 electrons. So it has a -1 charge, which is like, so its outer shell now looks like neons, all right? And so that is what happens when ionic compounds are made. You're going to have positive ions and negative ions connecting, okay? So that's where those charges come from. And then what you're going to learn is the total charge of a compound, an ionic compound, must be 0. So the charges have to cancel out. Now, when I've got that, like if I have potassium forms a +1, and if I put that with sulfur is a -2. All right? So there's 2 ways to look at it. One, you can say, okay, if you multiply the subscript, which is the number of atoms, times the superscript, that's going to give you the total charge of that side. So how many K's +1s do I need to cancel out a sulfur that's a -2? I would need another one, right? Because I need 2 +1s to cancel out 1 -2 charge. Everybody see that? And so, if I need that, it's going to be K2S. I need 2 potassiums to cancel out 1 sulfur, which has a -1 charge, or -2 charge. Now, the other way to do it is called the crisscross method. So I can take the number, not the charge, just the number, and throw it here. I can take the number, not the charge, just the number, and throw it there. Then, so you crisscross the oxidation numbers and reduce. Can I reduce 2 and 1? No. So then it's written correctly as K2S. So that's kind of a cheat way to do it. It's like it's just crisscross and reduce. It will always give you the lowest common denominator. And you can check it because the total charge has to be 0. And the total charge is made up of the subscript times the superscript. So 2 times +1 gives me what? +2. 1 times -2 gives me -2. So those cancel out, so that means you did it correctly because the total charges have to be 0. Now, so it's written correctly, but then I have to name it, all right? So how do I name ionic compounds? When you name ionic compounds, the metal will keep its name, so whatever it is, that's its name. So in this case, it's just potassium. And then sulfur, okay, is going to change into IDE ending. So it's sulfide. So it's potassium sulfide. And that's how you name it. The metal keeps its name. The non-metal changes to IDE. All right? Now, one thing that's important to understand with ionic compounds is they follow what's called the law of definite proportions, which means there's only one way to write the compound because the charges have to cancel out. So if I have Mg and F together, like on that example, I couldn't have, Mg3F2 or Mg5F7, all right, the only way I can write it is MgF2, and that's because I have a +2 and a -1 charge, crisscross and reduce, the total charges cancel out. So MgF2 is the only way to write it, because that's the only way the charges will cancel out. So that's called the law of definite proportions. All right? Now, when you're naming them, all right, the easiest ones to name are when the metals are in the first two families, because these are always our +1s. Lithium, potassium, all the way down, always +1s. These are always +2s. But when you get into the transition metals and underneath the staircase, their charges can vary. So because of that, you have to use a Roman numeral to show the charge. So if I have, Fe, and if I have FeO, all right? Well, I know oxygens are -2, and it's a 1-to-1 charge, so what does iron have to be? It has to be a +2, right? Because the charges have to cancel out. So when I write the name of that, I write the name iron, just like any metal, you keep its name, but I have to write the charge of iron in a Roman numeral in parentheses. So it's iron 2 oxide. Now I don't have to do that for sodium or potassium or any of that, because I already know that sodium can only be a +1. So I don't need to write a 1 there, okay? I just put sodium in oxide, if it was oxygen, with oxygen, all right? Now remember, the other thing is, this Roman numeral stands for the charge of the metal. It does not stand for the number of atoms of the metal. So if you're given iron 2 oxide and you're expected to write the formula, then you just write iron, and then 2 tells me it's +2, and then oxygen, I know oxygens are -2, so 2 and 2 reduced to 1-to-1, so it's just FeO, and you're done. A lot of people mess it up though, and they see iron 2, so they throw a 2 down there. You don't put a 2 there, okay? This stands for the charge, which is the superscript, not the number of atoms, which is the subscript, all right? So the harder ones to name are the metals that are Roman numeral metals, only because you have to tell the charge with the Roman numeral. But I think it's actually easier when they give you the formula. Like if they give me, tin 4 sulfide, then it's Sn is 10. It tells me it's a what? +4, and then it's with sulfur. Well, sulfur is an oxygens family, so it's a -2. So then you crisscross, so 4 here, 2 here. Remember, you don't cross the charges, just the numbers. So 2 and 4. And then can I reduce 2 and 4? Yes, so it's going to be 1 to 2. So it's Sn1, S2. So tin 2 or tin 4 sulfide, the compound is written like that. All right? And remember, the whole point of this is you're taking metals and you're combining them with non-metals. But how do I do that? Well, I have to crisscross the charges, and they have to cancel out. How do I name them? Metals keep their names, non-metals change to IDE. And there's only so many non-metals you can have. So it's fluoride, chloride, bromide, iodide, oxide, sulfide, selenide, telluride, nitride, phosphide, arsenide, carbide, and siliconide. Those are the only non-metals that you can even have. So those are the ones you're going to use over and over again. The more you write it, the better you get. Because you cannot put oxenide, it's oxide. You can't put sulfuride, it's sulfide. So you need to know that because you need to write them correctly. So today in class, you're going to be naming ionic compounds and writing formulas for ionic compounds. All right? Boom.